Alright guys, in this section we're going to be discussing increasing and decreasing functions and the first derivative test. We will learn how derivatives can be used to classify the relative extrema that we defined in the previous section as either relative minimum or relative maxima. But first it is important to define increasing and decreasing functions. Okay, here we have our definitions. A function f is increasing in an interval when for any two numbers x1 and x2 in the interval, x1 less than x2 implies that f of 1 is less than f of x2. Similarly, for a decreasing function on an interval, for any two numbers x1 and x2 in the interval, x1 less than x2 implies that f of x1 is greater than f of x2. So there's a little typo in there, guys. It's not less than, but greater than. Okay? So here's a diagram that represents increasing and decreasing functions and also constant functions. So consider this function f here, and notice how coming from negative infinity all the way to the point x equal to a, the function is decreasing. Then from point a, x equal to a, to point x equal to b on the x-axis, the function is constant. And then from point x equal to b to infinity and the x-axis, the function is increasing. You can quickly see that from a picture. We can see how the function is decreasing, starts out decreasing. And notice how if we were to compute those slopes on the decreasing and increasing part, you'll see how the slope of the tangent line in that section are going to be negative, right? And the slope of the tangent lines on the part where it is increasing are going to be positive, right? And obviously slope on the constant part is 0. So we already know the derivative is what represents the slope of the tangent line at any given point. So now we can make the connection of the derivative telling us whether a function is decreasing or increasing or constant over some interval. We put all this together into a theorem for test for increasing and decreasing functions. And we have a function f defined with some closed interval a to b and differentiable on the open interval. Right? The derivative greater than 0 for all x in that interval implies that f is increasing on that interval. If the derivative is negative, less than 0 on that interval for all x's in that interval, then the function is decreasing. And if the derivative is equal to 0 for all x's in that interval, that implies that the function is constant there. So now we don't have to look at a picture. We can just evaluate the derivative and determine the sign of the derivative on a given interval to determine whether the function is increasing or decreasing. Here we have a couple of guidelines for finding intervals on which a function is increasing or decreasing. So having a continuous function on the interval a, b, we use the following steps to find whether a function is increasing or decreasing. First, we want to locate the critical numbers so that we use those to determine test intervals, and we'll see that in an example in a minute. Then we determine the sign of the derivative of f at one test value on each of the intervals. We're going to use the theorem from before to determine whether it's increasing or decreasing on that interval based on the sign of that derivative, okay? And then we'll write the intervals accordingly. So here we have an example. And we're asked to find the open intervals in which the function is increasing or decreasing. And this is a nice quadratic here. F of x equal to x squared minus 2x minus 8. So following the guidelines here, we're going to start by finding the critical numbers first. Now remember, we've defined what critical numbers are before. And that's when the derivative is equal to 0 or undefined. Since this is a nice polynomial, we don't have to worry about the derivative being undefined because it's not going to be undefined. We get a linear function here for the first derivative equal to 2x minus 2. So we just need to find when this derivative is equal to 0. So setting that equal to 0, factor the 2 out. We can get rid of the 2 there and solve for x there. So x minus 1 equal to 0. We set that factor equal to 0 and we get that x is equal to 1. In this case, we get only one critical number, and that's at x equal to 1. All right, once we found our critical number, we're going to go ahead and set up a number line here. And notice how since we have only one critical number, we just get two sections here. This whole number line is split into two right there at 1, and we just want to take one number within each interval to test it on our derivative. So I'm going to pick some numbers in here just to keep it simple. I pick 0 on the left interval and 2 on the right interval. And notice how once I evaluate those two x's or those two x values on the first derivative, I get -2 for 0, which is negative. So that whole interval, the function is going to be decreasing on that whole interval from -infinity to 1. And then I get 2 for f prime of 2, the derivative of f at 2. I get 2, which is positive, so I represent that whole interval is going to be increasing from 1 to positive infinity. All right, so then writing this in interval notation, I get that f is decreasing, function f is decreasing from -infinity to 1. And we get that f is increasing from 1 to infinity. Okay, here we have another example. F of x equal to sine of x minus 1. And we only want to consider the function from 0 to 2 pi exclusive, not including 0 and 2 pi. As you know, sine function goes on forever. If we don't restrict our domain here, we'll have an infinite amount of intervals where it increases and where it decreases. So we're going to restrict our domain to go from 0 to 2 pi exclusive. Our first step is to find the critical values, and we do that by finding the derivative of this function. The derivative is just the cosine of x, and since this is cosine of x is defined everywhere, we don't have to worry about setting the derivative equal to undefined or figuring out when the derivative is undefined. Just finding when the derivative is 0 will suffice, and that happens when x is equal to pi halves and 3 pi halves. So here we have our critical numbers. All right, so plotting these points in our number line here, and remember we're only going from 0 to 2 pi, and I'm putting parentheses at the endpoints there to just indicate that we're not including 0 and 2 pi. Then I indicate my critical numbers in the number line. I have pi halves and 3 pi halves. I'm gonna pick one number within each interval. So notice how I have 3 intervals here. One going from 0 to pi halves, the other one going from pi halves to 3 pi halves, and the other one from 3 pi halves to 2 pi. So I'm going to pick just one test value from each. As long as it's within each interval, it will work. So I'm picking pi thirds, because pi thirds happens to be between 0 and pi halves. Again, it doesn't matter which one you pick, as long as it's within that each interval. I'm just trying to, for simplicity, trying to pick values that I'm used to so that it'll be easy to evaluate. And then in the second interval, I'm picking pi, and then 5 pi thirds on our third interval. So these 3 test values, I'm going to go ahead and plug those into our derivative to figure out the sign. Remember, we're using the theorem from before, where if the derivative is negative, then that means the function is decreasing. If the derivative is positive, then the function is increasing. All right, so evaluating pi thirds into our first derivative, we get that's equal to cosine of pi thirds, which is just 1/2. It's positive, okay? So let's go ahead and figure the other two, and then we'll indicate that in our number line. Derivative f prime of pi is equal to cosine of pi, and that's equal to -1, negative. And f prime of 5 pi over 3 is equal to cosine of 5 pi over 3 equal to 1/2, which is positive. Okay, so looking at the signs here, I can indicate how for the first interval, I'm going to have the function increasing from 0 to pi halves. The second interval, I have the function decreasing, and the third interval, I'm going to have the function increase again. All right, writing this formally, we have that in interval notation, we have that f is decreasing from pi halves to 3 pi halves, and again, we always represent this with an open interval, and a function is increasing from 0 to pi halves, and we can represent it with a union here from 3 pi halves to 2 pi, and there we have it. All right, so our next big theorem here is going to be the first derivative test, and we're going to use the first derivative not only to identify when the function is increasing or decreasing, but use that too to indicate extrema. And what this theorem is saying is, if we have a critical number c on a function f that is continuous on an open interval I containing this c, if f is differentiable in that interval except possibly a c, then f of c can be classified as follows. Okay, if the function f, if the derivative of the function, in other words f prime of x, changes from negative to positive at c, then we have a relative minimum at that point, c comma f of c. If the derivative changes from positive to negative, then we're going to have a relative maximum. Now, if the function goes from positive to positive when it goes through that point C, or negative to negative, then f of c is neither a relative min or a relative max. Okay, here we have an example where we're going to follow the steps here of what we've been doing, and we're going to find a couple of things here. So the problem is breaking it down so that you know exactly what to do to find those extrema using the first derivative test. We have in the following examples, we have first we want to find the critical numbers of f, if any. Find the open intervals on which the function is increasing or decreasing, which what we did last on the previous examples. Apply the first derivative test to find or identify all the relative extrema. And then we're going to use a graphing calculator or utility or the computer to confirm our results. So we have this function f of x equal to negative 2x squared plus 4x plus 3. Another nice quadratic here. So the first thing we want to do is find the critical numbers, and we do that by finding the first derivative and setting that equal to 0. Again, because this is a nice polynomial function, we don't have to worry about the undefined. We just set the first derivative equal to 0 and find those critical numbers. Factoring the negative 4, we get that x minus 1 is going to be equal to 0. From there, we get the 1. That x is equal to 1. So once again, we have only one critical number here, namely x equal to 1. At x equal to 1. All right, putting this in our number line, we're going to figure out our intervals where the function is increasing or decreasing. And we've been practicing this on this last couple of examples. We just have one critical number, split the number line in two, choose a test value on each side or on each interval that we have, and we have 0 and 2. I'm going to plug those values into our first derivative and figure out the sign of the derivative there. We get 4 for f prime of 0 and negative 4 for f prime of negative 2. So we have positive and negative. So the function is increasing, coming from negative infinity to 1, and then after 1 is going to start decreasing. Right? So formally, using our interval notation, we have that f is decreasing from 1 to positive infinity and increasing from negative infinity to 1. Okay, next, we're going to apply the first derivative test to figure out or determine whether that 1, our critical number 1, is either a max or a min. Let's use the theorem here that we just discussed, the first derivative test, to determine whether we have a max or a min. And we do that by looking at the signs here. We're coming from, look to the left of 1 on the number line. It's plus going to a negative. In other words, it's increasing, it's changing to decreasing. So if you look at your theorem, at your first derivative test, if the function changes from increasing to decreasing, in other words, the first derivative, the sign of the first derivative goes from a positive to negative, then we're going to have a relative max right there at x equal to 1 at that critical number. So then the point, the order pair would be 1 comma the function evaluated at 1. That would be your order pair. If you want to do that on the side, you can. So f of 1, just plugging in 1 into your function, not the derivative of the function, because the derivative is equal to 0 at 1. So what is the y value when x is equal to 1? Just plug that in, and we get that f of 1 is equal to 5. So then our relative max is 1, 5. All right, well, checking our results here on the graphing utility, we can just graph this quadratic, right, or whatever function we're given, into our y equals here in the calculator. So we plug it in here, negative 2x squared plus 4x plus 3, and then just hit graph, see what we get. There we gonna have a parabola there. And notice how we only have one extrema here. There's not gonna be a min because, right, the parabola opens down, so it just goes to infinity. You can see that from the picture. If I do second trace to figure out my max, give a left bound and a right bound and enter, I get the maximum 1, 5. Here's another example where we have f of x equal to x minus 2 sine of x. And again, because we have this trigonometric function here, or trigonometric portion of it, we know that if we don't have a restricted domain, it's going to keep going forever and ever. So we're going to just look at this function from 0 to 2 pi and not include those endpoints. So finding the critical numbers, the same procedure. Find the derivative first, and set it equal to 0. Again, we don't have to worry about this being undefined because cosine is defined everywhere. Solving for cosine, we get cosine of x is equal to 1/2. Therefore, x will be equal to pi thirds and 5 pi thirds. Here we have our critical numbers, and now we plot those into our number line, just like we've done before, and we're going to choose some test values here within each interval. Always try to pick values that are easy to evaluate. So I'm choosing pi fourths between 0 and pi thirds. Pi fourths isn't there. Then between pi thirds and 5 pi thirds, pi is in the middle of it. And then we have, I'm going to choose 7 pi fourths between 5 pi thirds and 2 pi. Those should be fairly easy to evaluate in our first derivative, which is our next step here. Plugging those values into our first derivative to figure out the signs and whether the function is increasing or decreasing on those intervals. All right, f prime of pi fourths is equal to 1 minus 2 cosine of pi fourths. We know that pi fourths is square root of 2 over 2 times 2. That's just square root of 2. So then this is equal to 1 minus square root of 2. You don't need to evaluate all this in the calculator. All we care about is a sign. But if you need to put in the calculator to double check or confirm, you can. 1 minus square root of 2 is a negative number. And that's all we care about, something less than 0. So then therefore, the function is going to be decreasing in that interval. Similar way, we do f prime of pi is equal to 1 minus 2 cosine of pi. Cosine of pi is negative 1, which turns that into 1 plus 2. And that's equal to 3. 3 is positive numbers, it's greater than 0. So it's going to be a plus there for that interval. And the last test value is 7 pi fourths. F prime of 7 pi fourths is equal to 1 minus 2 times cosine of 7 pi fourths. And it's going to be actually the same thing as the first one here. We're going to have 1 minus square root of 2, which is also less than 0. So then this function is going to be from 0 to pi thirds is going to be decreasing, negative sign there. And then on the next interval from pi thirds to 5 pi thirds, it's going to be increasing, and then it's going to decrease again from 5 pi thirds to 2 pi. Now we're going to apply our first derivative test to determine whether we have a relative max or a min. And when you see the signs, when the function is going from decreasing to increasing, you have a relative min there. So pi thirds will be a relative min, and 5 pi thirds will be a relative max, since the function is increasing on the left of 5 pi thirds and then decreasing after on the right of 5 pi thirds. It's all about the change that happens from the left to the right of that critical number. And you can write them as ordered pairs. I left them in exact values, but we get that. Now, of course, we can confirm this with our calculator here, and you just plug in the function in your y equals, and we have y equals x minus 2 sine of x, and we get this function here, but we only care about the windows, our domain from 0 to 2 pi, not inclusive. So we're going to fix our window to go from 0 to 2 pi, and change your x accordingly, and I can modify my y so that I get a nice window. But once I fix my window, you can see how the min and the max there, one at pi thirds and the other one at 5 pi thirds, confirming our results. And there we have it.